The lecture 23. This is the first of two lectures that are going to cover chapter 27 or topic 27 as your book names them. And this is on the topic of quantum physics. In this lecture, I'm going to go over the historical approach of where quantum physics came from, how physicists arrived at the theories of quantum mechanics or quantum physics. I will also discuss some of the key ideas, key findings, of course, and the formulas that we will be using in order to solve some simple problems about quantum physics. In the second lecture that's going to cover this chapter, chapter 27, and that'll be lecture 24, I'll show you a few examples, and I'll be posting that next week. All right, so let's get into an introduction of quantum physics. So the reason that I take more of a historical approach, and your book does as well, is because we're not going to be deriving all of these theories in the same way that we would derive theories of mechanics or even optics or thermodynamics. We can't really take all of them back and build them off of, say, the theories of Newtonian mechanics and so on. Instead, there's a certain level of complexity here, and to not make the material just seem like it was handed to you, it's good to sort of show this historical progression so you see kind of the justification and the building up of ideas that gets us to things like the uncertainty principle and Schrodinger's waves and so on. Okay? And so it turns out that it all starts with something called blackbody radiation. So you can really think of this as the historical origins of quantum mechanics. So let's get into defining that. All right? So it turns out that an object at any temperature emits electromagnetic radiation. For example, we glow in the infrared, although we cannot see it with our eyes, but an infrared camera could see that we are glowing, as are most objects on Earth's surface. This is called thermal radiation, that glowing, that emitting of light. The spectrum of the radiation depends on the temperature and the properties of the object. At low temperatures, the wavelengths of the thermal radiation are mainly in the infrared region, right? So that would be, and you can go lower than that. You can have things that are so cool that they're creating microwaves. For example, you can have these very cool gases in the universe that create microwave radiation. And however, as the temperature of the object increases, the object eventually begins to glow red, then white, and then eventually will continue to glow more in the blue spectrum. Okay? And so thermal radiation consists of a continuous distribution of wavelengths from the infrared, visible, and then all the way up into ultraviolet, and so on. Okay? So, according to classical physics, thermal radiation originates from the acceleration of charged particles near the surface of an object. Okay, so these charges emit radiation similar to the acceleration of charges in an antenna. Okay, so this is classical physics in the sense of a classical electromagnetism. So this would be electromagnetic induction in the same way that we justified the existence of EM, electromagnetic radiation, as light. Right? We said that if a charged particle is accelerating, then it's going to be creating a changing magnetic field because the magnetic field is proportional to the velocity of the particle. So if the particle's velocity isn't remaining constant, neither is the strength of the magnetic field surrounding that particle. And if the magnetic field is changing in any way, then the flux through any particular area must be changing. Thus, that changing magnetic field creates a changing electric field. But of course, that changing electric field in turn creates a changing magnetic field, and you've got the idea of a self-propagating wave known as light. Now, that probably seems kind of like a modern idea since that's electricity and magnetism, and certainly is more modern than things like Newton's laws or Galilean relativity or things like that. However, it is still considered a classical theory. Okay, so we've moved past classical electromagnetism into modern physics. Quantum mechanics takes classical electromagnetism and changes it. It reveals things that Maxwell's equations, Faraday's law, Gauss's law do not correctly anticipate. Okay? So, the charges, those accelerating charges, can have a distribution of frequencies. And that would account for the continuous spectrum of radiation emitted by the object, right? Because there's no one particular frequency that they're going to be accelerating at, right? They're going to be all the atoms and molecules are going to be doing a bunch of different things in any given object. Think about them vibrating and bouncing around. Okay? So by the end of the 19th century, however, physicists realized that classical theory of thermal radiation wasn't working. The basic problem was in understanding the observable distribution energy as a function of wavelength. Or the function of wavelength in the radiation emitted by a black body. And quick thing here, what is a black body? What is the definition of a black body? Well, a black body is just a perfect emitter. Okay, so it would have an emissivity of 1. It is a perfect absorber and a perfect emitter of light. It absorbs all light incident upon it, so it would appear black in color because it's not reflecting any light. It has no reflectivity. It's not shiny at all, and so that's a perfect black body. Obviously, any colored object is not a perfect black body, but it's a pretty good approximation. Even things like the sun, you might be like, oh, well, that's a big ball of gas. That can't be a black body. It's not even solid. Actually, does work pretty well as an approximation of a black body. So stars definitely fit that criteria of being black bodies. Things that don't would be like a shiny metal, for example, something that is particularly reflective. That's what would not be a good example. Or any very loosely packed gas. So a star is an incredibly dense ball of gas or plasma because it's ionized gas. But like a nebula in space or the atmosphere of Earth would not be good approximations of a black body because it's much lower density gas. Okay, but hopefully you understand then what we mean by a black body. It's a solid and it absorbs all colors, or at least many of the colors. Okay, so many wavelengths of light are absorbed. Okay, so you can think of a good approximation, we'll flip back to the previous page, of a black body as a hole in a hollow object. Okay, so the nature of the radiation emitted through the small hole depends only on the temperature of the cavity walls, not at all on the material composition of the object, its shape, or anything else. Okay, so essentially it is dependent only on the temperature. Okay, that's all that's going to matter for how much, because you think about what's coming out of that hole, right? Well, it's just a bunch of trapped particles bouncing out, and it only depends on how energetic they are. So that would be the temperature of the particles. And so then the ones that bounce out are only going to depend on how much they're bouncing around in the first place, right? So as the particle bounces around in here, we're saying that it's independent of any of the properties of the bounce and only depends on how frequently it bounces back and forth. Okay, so that's actually kind of the underlying theory. So that means that sort of on some sort of conceptual level, black bodies are a series of cavities. Okay? So experimental data from the distribution of energy in blackbody radiation at 3 temperatures is shown in this figure. We have the 4,000 Kelvin, 3,000 Kelvin, and 2,000 Kelvin. They all have their own distinct curves. So the radiated energy varies with wavelength and temperature. So as the temperature of the black body increases, the total amount of energy it emits, that's the area under the curve, increases as well. All right? So the curve has a different peak location and it has a different area, and the area gets larger as the temperature gets larger. So in this case, the 4,000 Kelvin by far has the largest area under the curve, thus telling us that there is more energy emitted by a black body that is glowing at a temperature of 4,000 Kelvin. So notice that with an increasing temperature, the peak of the distribution shifts to shorter and shorter wavelengths, as I mentioned. The shift obeys the relationship that is called Wiens Displacement Law. Okay? And Wiens Displacement Law is right here. Okay? So this formula in a box is Wiens Displacement Law. It's an empirical law that's based on observation. Okay? And so it tells us that lambda max is going to be based on the temperature of the object. It's absolute temperature because we're using a Kelvin scale, which is an absolute scale. So I could then solve for lambda max, or I could solve for T depending on the problem. Okay? But that's all that it's dependent on. So if you see a particular wavelength, peak wavelength that's emitted by an object, you know the temperature of that object. Okay? Or vice versa. If you know the peak wavelength, then you can find the temperature. Or if you know the temperature, you can find the wavelength, excuse me. Now, down below is so this down here is for the particular case of an object that has a temperature of, we have here, or actually has a wavelength emitted at 2.3 times 10 to the negative 7 meters, which would be equivalent to 230 nanometers. So if there is a particular object that is glowing at a color that corresponds to 230 nanometers, then we would know that the temperature would be 12,600 Kelvin. Okay, so that would be one example, which would be significantly hotter than the 4,000 case, and would actually have a peak, since this peak of 230 nanometers is actually ultraviolet. That would be an object that is glowing in the ultraviolet side of the spectrum. Okay. So stars often fall in the visible spectrum. That's why we've evolved to see visible light, because the peak wavelength falls in that spectrum. In fact, you can think of, let's just take a look at these curves, right? So these curves are color-coded, not because that's the color that they glow at, but just to distinguish one curve from the other. But if you look at the one that's 2,000 Kelvin, what color would that appear? Well, it would appear a very faint red color, because the highest intensity light is in the red. Now the peak is well into the infrared, because we're over here on longer wavelengths is the infrared, shorter wavelengths being the ultraviolet. And so you might be like, well, the peak is firmly in the infrared. Why would it be visible in the red? Because it's still not zero at red, but it's greatest at red. Even a better example is the 3,000 Kelvin. An object that has a temperature of 3,000 Kelvin would appear red. Even though the peak is in the infrared, it's still fairly high in the red, and it falls off precipitously, so there's not nearly as much blue light. So the overall effect might be a little orange, but it's going to be predominantly red. If we move this peak actually into the visible spectrum, so if I had a curve that had a peak right at yellow, well, then I'm going to have a good amount of symmetry around the peak. So that means that there's going to be just as much indigo, blue, and violet light as there's going to be red and orange light. And what ends up happening is that as the composition of all those different colors with a peak that's right in the middle at, say, green, then the effect is light that appears white. So in fact, our sun, which appears white because it has just as much blue, shorter wavelength light, and red, longer wavelength light, because there's a peak right in the middle, means that the actual peak wavelength of our sun is green. So it's kind of fun to think of it that our sun is actually green. Right? If you were to describe the sun by its peak wavelength, its maximum lambda, then you would say that it is a green star. But the appearance, of course, is white. Okay, so let's look at, again, the same graph. And by the way, the axes here were intensity as a function of wavelength. All right, that's the intensity of light. And that's why when we say peak wavelength up here, it's because that's the particular wavelength that has the most photons at that wavelength. That's our lambda max. It's the most frequent of a particular wavelength. Okay? So here we're looking at a figure that shows the experimental plot of the blackbody radiation spectrum. So the blue curve, okay, together with the theoretical picture of what this curve should look like based on classical theories. Notice they don't agree. Okay, so this is something I mentioned a second ago. So that sort of brownish orange colored curve is the one that is the experimental curve, right, as it's labeled. Okay, and so at long wavelengths, classical theory is in good agreement with experimental data. So over here we have good agreement, but they begin to deviate as we move towards the ultraviolet. So notice at the shorter wavelengths, there's a major disagreement between the classical theory and the experiment. As lambda approaches zero, classical theory predicts that the intensity should go up infinitely, whereas the experimental data shows that it definitely doesn't. This is, if you've heard the term, this is called the ultraviolet catastrophe, which is just a fun name. It's just the idea that this was a big problem in physics because it really demanded a good explanation that wasn't being presented by anything that electromagnetism or classical mechanics allowed us to understand. You know, the fact that the curve fell back off with these higher wavelengths, it just seemed very strange because, of course, these lower wavelengths, higher energy photons, because you'd think with these very high energy photons, which are the short wavelengths, the ultraviolets, the X-rays, and so on, that though that type of light should create, it should be, should create a huge amount of intensity, but it doesn't, right? So why is that? What is happening? So in 1900, Planck, okay, it's a name we're going to hear quite a bit, developed a formula for blackbody radiation that was in complete agreement with the experiment. So he found a theory that predicted this blue curve here, okay? And in order to get the theory to match the experiment, Planck had to hypothesize that blackbody radiation was produced by tiny submicroscopic charged oscillators, which he called resonators. He assumed the walls of a glowing cavity were composed of billions of these resonators, almost like tiny little chambers, like I said, although their exact nature was unknown. The resonators were allowed to have only certain discrete energies given by the relationship shown. Okay, and that's this relationship here. Okay? N is a positive integer called a quantum number. Okay, so N is our first quantum number. We're going to see quite a few quantum numbers. F is the frequency of the vibration of this theorized resonator, and H is a constant known as Planck's constant. Okay, and he had to kind of fit that constant. So he basically took the curve and found the constant at work. So the Planck's constant is an empirical constant. It was one that has been fine-tuned in order to fit measured values of the universe. Okay, measured behavior, phenomenon of the universe. Because the energy of each resonator can only have discrete values, we say that the energy is quantized. Each discrete energy value represents a different quantum state, with each value of n representing a specific quantum number. Okay? So the key point in Planck's theory is the assumption of quantized energy states, because this is a brand new idea. No one had ever thought to say that anything could only have particular energies. We're used to energy being a continuum. Okay, this was a radical departure from classical physics, because it would be like saying that if you threw a ball, you could only throw that ball at particular velocities. You could throw it at 5.6 meters per second or 5.7 meters per second, but it was physically impossible to throw it at 5.65 meters per second, halfway between 5.6 and 5.7. Okay, so it's such a strange idea, such a brand new idea, and it was one that Planck was not sure was real. Perhaps it was just a stopgap, fitting the data, and was maybe we want to reveal something about classical physics that we didn't yet understand. Okay? But it turned out that this idea of quantized energy states was actually real and was going to allow us to see the universe in a whole new way. Okay? And by the way, this is Planck's constant. This is accurate to four significant figures. You can find it to more significant figures, but this is a value. Planck's constant represented by the letter H. Okay? So now comes Einstein. Okay? Because again, Planck was skeptical of his own theory, not that it didn't work well for predicting behavior, but that it wasn't explaining the true underlying physical nature of the universe. Well, it turned out that the photoelectric effect, an experiment by Frank Hertz, would be used by Einstein to show that quantization was in fact the reality we lived in. Okay? So in the late 19th century, Hertz discovered that light incident on certain metallic surfaces caused the emission of electrons from the surface. So you realized you could free electrons by bombarding a surface with light, basically, heating it up with particular frequencies of light. This phenomenon is known as the photoelectric effect. All right? And it is the emission of electrons, and the electrons that are emitted are called photoelectrons. Okay? So you can see when light strikes plate E, the emitter photoelectrons are ejected from the plate, shown here, and the electrons move from the plate E to plate C, the collector, creating a current in the circuit, registered at the ammeter. And that's how we knew that electrons are being created, because there's nowhere else they could have come from. They had to pass this vacuum gap, and there you have it. We were able to show that electrons could be freed from a metal. That in itself was quite interesting, but now we're going to use that idea to explain something even more interesting. Okay? So a tube like this, when it's kept in the dark, will give zero current. That indicates that there are no electrons being ejected from the metal. However, when the plate E is illuminated by light having a wavelength shorter than some particular wavelength, come back to the idea, and that wavelength will depend on the material, so different materials have different wavelengths, a current is detected by the current meter, the ammeter, okay? And that's shown here as A. That's the ammeter, a meter that measures current, okay? And the current arises from those photoelectrons that are being energetically broken free from the metal and then collecting on the collider, because they had so much kinetic energy that they made this gap. They flew across, they crashed in the collider. Obviously, trillions upon trillions of these electrons would do this for the right intensity light, again at a particular wavelength, and then that's going to create a current, a flow of electrons. Okay? So, let's take a look at this plot. This is continuing the idea of the photoelectric effect. Okay, so we're looking at current as a function of applied voltage. So the plot of the photoelectric current versus the potential difference, delta V, between the two plates, the E and C plates, for two different light intensities. Okay, so this is for high intensity light and low intensity light. Okay? At large values of voltage, so a big voltage gap between the two plates, the current reaches a maximum value. Okay. Also notice that the current increases as the incident light intensity increases, as you might expect. Okay. So there's greater current with greater intensity. Okay, yeah, it makes sense, right? Probably just more electrons being freed because there's just more photons. Okay. So more light. Finally, when delta V is negative, that is when the power supply in the circuit is reversed to make the E plate positive and the C plate negative, that would start repelling the electrons, right? The current drops to a low value because most of the emitted photoelectrons are not energetic enough. They're repelled by the plate until eventually the current completely disappears. Okay? So in that situation, only electrons having a lot of kinetic energy would make it. So when delta V is equal to or more negative than the stopping potential, no electrons reach plate C, and the current is zero. The stopping potential is independent of the radiation intensity. The maximum kinetic energy of the photoelectrons is related to the stopping potential through the relationship shown here, okay, in the graph. So what we're looking at here, again, right, is that we have here the stopping potential. That's going to be energy per charge. That's a volts. Energy per charge, joules per coulomb. And so then if we think of the joules of an electron, then we can find out exactly how much kinetic energy an electron would need in order to make it from one plate to another. When we've reversed the polarity of the circuit, when we're running a voltage, or we've created the voltage that is going to be essentially stopping many of the electrons, and eventually, when we reach the stopping voltage, stopping all of the electrons. Okay? But look at the two curves we have here, the orange curve and the blue curve. The only difference between them is the intensity, and that does create different amounts of current, but both the currents fall to zero at the same point. And that was the part where I said it was independent. So the idea, again, is that the stopping potential is independent of the intensity of the light. Okay, so that's interesting. Why would it be independent? It seems like maybe more intense light would create more energetic electrons, but it doesn't seem to. So why? Okay, so here is the relationship. The maximum kinetic energy of the electrons is simply, since voltage is joules per electron, we just multiply by joules per coulomb, we just multiply by the number of coulombs in an electron, and that is exactly the energy an electron would need in order to make the gap. Okay, so now let's compare, because again, this whole idea of the photoelectric effect is going to allow us to think about the wave theory of light, which is the classical theory, the one that classical electromagnetism predicts, and then the observations that are actually being made, like the fact that the stopping potential is independent of intensity. Okay, so let's summarize our comparisons here. Okay, so the first prediction by the wave theory is that the photoelectric effect should occur at any frequency. However, the observation shows that no electrons emitted for a frequency below a particular frequency are actually, are created. There are no electrons freed if the frequency is too low. Okay. Now again, that's it. The wave theory says that, a wave is a wave, and it should, if you just, let a wave wash for long enough, then it's going to impart a certain amount of energy, and that energy has to go somewhere, and so that energy would have to then go to an electron and free an electron. Okay? But that doesn't appear to be happening. Okay? Another prediction. Light intensity increases, therefore the kinetic energy of the photoelectrons increase. We see that, in fact, the maximum kinetic energy of freed electrons is totally independent of the intensity. And we know that because the maximum kinetic energy is going to be equal to the stopping potential times the charge in an electron, and we saw that that was independent of the intensity, and that was an observation that was made in early experiments with the photoelectric effect. Okay? Another prediction. There should be no relationship between the photoelectron energy and the light frequency. Okay? Well, turns out that's not the case. The light frequency increases, or as light frequency increases, the maximum kinetic energy of electrons also increases. Okay. And so again, why is that? Why should there be no relationship between the photoelectron energy and light frequency? Well, because the electrons are going to get, again, if you think of this as a wave, that there's still going to be things getting washed away by the wave, no matter what the amplitude of the wave is. Okay? And then our last prediction, photoelectrons need time to absorb incident radiation before escaping from the metal. Because the idea, again, is that the wave is kind of continuous. It's washing over the metal, imparting some energy. That energy is going to go to energizing all the electrons until eventually some of them start wiggling so quick that they wiggle free. Okay, but the wave is still washing over, just giving more and more energy the longer it goes. And that also means that it shouldn't be instantaneous, because you need enough full waves to wash over the metal in order to heat up the metal enough to start freeing electrons. But in reality, the electrons are emitted almost instantaneously. So there's a lot of things here that we observe with the photoelectric effect that really fly in the face of the wave theory of light. So something is going on. Light is not behaving like a wave. Okay? So, in 1905, Einstein explained the photoelectric effect in a paper. This is the same year he published his special theory of relativity. Busy year for Einstein. Okay? So, Einstein predicted or extended Planck's concept of quantization to the two electromagnetic waves, okay? Not just these little resonators. He suggested that a tiny packet of light energy, or a photon, would be emitted when a quantized oscillator made a jump from an energy state En, and that's just a quantized energy state, so E sub n, n being our quantum number, to the next state, okay, the next lower state, En minus 1, where h is Planck's constant and f is the frequency of the light, which is equal to the frequency of the Planck's oscillator. Okay, so from the conservation of energy, the decrease in the oscillator energy, hf, must be equal to the photon's energy E, and the result is given here. Okay. So we have a direct relationship between the energy of the incident photon and the energy of the oscillator. So E equals HF. And so E1 would equal 1 times HF, E2 would equal 2 times HF, and so on. Okay? So, therefore, we can say that phi is called the work function of the metal, because that's how much energy it took to penetrate the metal. So let's think about this, right? Because again, this is the energy of the incident photon, which is equal to the energy of the resonator. Okay, so right, this one and this one. So incident photon comes in, matches the energy of the resonator, and then it's able to cause the resonator to do something. Okay, and one thing it does is it frees an electron. And it frees an electron with a certain amount of kinetic energy. Because again, this is the kinetic energy of the electron, at least the maximum of electron. And so then phi, not an angle here, but just a variable, is actually a quantity that would have units of joules, okay? And that is the work function of the metal. That's how much energy it took, like I said, to penetrate the metal. Because not all the energy is going to the kinetic energy of the electron. Some of it was absorbed by the metal. Okay? And that makes sense because the metal does heat up in addition to emitting energetic electrons. And so we see here that we have some work functions for common metals, right, such as aluminum and copper and so on, right, zinc, and they're all in units of electron volts. An electron volt is equal to 1.6 times 10 to the negative 19 joules. It's just a convenient unit of measurement for such small values of energy. Okay, so let's continue on with the photoelectric effect, with explanations rather than just observations. So as remember, right, these were the observations that we had, the ones that seem to contradict what we'd expect from waves. So what is the best explanation then? How do we go then from thinking about light as a wave to thinking about light as something else? Of course, light as a particle, as a photon, as a quantized packet. Okay, so no electrons emitted for a frequency below Fc. Well, the explanation is that photoelectrons created by absorbing created by absorbing a single photon. And the photon energy has to be greater than or equal to the work function. Otherwise, no free electron. Oh, that's interesting. So that means that there's a one-to-one. Every photon of light interacts with one electron only. They're acting like particles. Okay? What about the fact that the kinetic energy of the maximum kinetic energy of freed electrons is independent of the light intensity? Well, that's explained by this theory here, that the kinetic energy is equal to the instant light energy minus the work function, which shows plain and simple that it's completely independent of intensity. Intensity is just how many photons are hitting the metal, not the properties of the individual photons. And the properties of the individual photons matter because every individual photon interacts with an individual electron. Yeah, see? Very different from a wave. Okay? The light frequency increases. As light frequency increases, the kinetic energy of the photons or the photoelectrons increases. Of course, that's what we see. Okay, and we see that the maximum kinetic energy of the electrons is linear in frequency. Okay. All right. So we see that there's a direct there's no relationship between intensity and photoelectron energy, kinetic energy, but there is a relationship between frequency and photoelectron energy. And that's because the frequency is what sets the energy of the photons that are colliding with the electrons. Okay. And now our last observation, electrons are emitted from the surface almost instantaneous. There's no delay, right? That was not wave-like. Well, that can be explained by the fact that the light energy is in packets. No time needed for electrons to require energy to escape the metal. Right? It's an almost instantaneous collision. It's not a slow buildup of energy washing over the metal. Okay, so let's take a look at this graph. So experimentally, a linear relationship is observed between frequency and maximum kinetic energy, as shown in this figure. Right? This is maximum kinetic energy of the freed electrons. This is frequency of the instant light. So the intercept of the horizontal axis corresponding to kinetic energy max of 0 gives the cutoff frequency below which there's no photoelectrons are being emitted, regardless of the light intensity. We can derive the cutoff wavelength, lambda c, as shown here. All right? So we just set up our relationship between the maximum kinetic energy of the electrons, the instant light energy of individual photons, minus the work function. If we want no electrons to be freed, that means that we're going to be essentially setting our incident light energy per photon equal to the photon energy. And here we've replaced F with C over lambda, and then we just solve for lambda. So this would be the necessary wavelength of light in order to free at least one electron from the metal. And see, it's dependent. I keep doing that. Excuse me. It's dependent on the on the work function of the metal, because certain metals just don't get penetrated that easily by light, and so if they have a larger work function, then we're going to need a larger lambda to or a lower wavelength to compensate. Okay, not a larger wavelength, a higher frequency. We need a lower wavelength, which means we need higher energy light, not higher intensity light, right? Because those ideas, they might seem interchangeable, but we're not talking about it. Again, intensity of light is number of photons. That's our way of thinking about it. Okay, energy of light is energy per photon. All right, so let's wrap up the photoelectric effect here. So a photocell shown in this figure is a device that exploits the photoelectric effect. The photocell produces a current in the circuit when the light of sufficient high frequency falls on the cell, but it doesn't allow a current in the dark. This device is used in street lights. A photoelectric control unit in the base of the light activates a switch that turns off the street light when ambient light strikes it. So this is a light sensitive sensor, right? That's what this is. This is it. This is this is the basic circuit design for anything, whether it's a night light or a street light, that turns off during the day and turns on at night. Okay? So pretty neat idea that can be employed so directly. Okay? So I intended to do one video, but I spent a lot of time talking about the photoelectric effect, so I'm going to stop this one, and I'll come back for a second video where I talk about the other sections in this chapter, which should be much more brief. X-rays, something called Compton scattering, and a few other follow-up topics. All right, well, thank you for listening.